everyone, and welcome to our today's class. It is our fourth and last lesson on the topic magnetization. So as usual, let me start by giving you the quote of the day, which states that the teacher has failed more times than the student has ever tried. The only difference is that the teacher chose a better meaning of the word fail, that is, first attempt in learning. So we'll discuss that quote at the end of our class today. So today we'll be looking about demagnetization. But before you understand what we mean by demagnetization, let's remind ourselves of what we mean by magnetization, because demagnetization is just the opposite of magnetizing. So from our previous class, we did say that magnetization is just the process of making a magnet from a magnetic material, the process of making a magnet from a magnetic material. Now we are saying that demagnetization is now the opposite of magnetization, meaning in demagnetization we'll actually be making magnets to lose their magnetism instead of making them. So demagnetization is defined as the process of making a magnet lose its magnetism. Demagnetization is the process of making a magnet lose its magnetism. Now we have basically two methods of demagnetizing a magnet or demagnetizing a magnetized material. So one of the method is what we call a material can be demagnetized by hammering, or sometimes what we call heating. Then a magnet can also be demagnetized by use of electrical method. So we'll see how. So let's start discussing by how to demagnetize a magnet by hammering and heating. So remember, we did say that hammering is just the process of heating a magnet or a particular magnetic material with a hammer. You just hit it several times. So to demagnetize a magnet using hammering method, the magnet is demagnetized by either heating in fire or hammering it several times while facing east-west direction. So this is our steel bar which has been magnetized. Then we are heating it, or we are hammering it while it is facing in the east-west direction. So if a bar magnet or a magnetized magnetic material, which of course has now become a magnet, is heated while it is facing in the east-west direction, it gets demagnetized. Also, if a magnetic material which has been magnetized is hammered or hit by a hammer several times while it is facing in the east-west direction, it also gets demagnetized. Now the magnetism is lost because mechanical hammering or heating disorients or disaligns the magnetic dipoles. So remember, we did say when we were discussing about the domains theory, we did say that anything that causes the dipoles to disalign or to disorient or to makes them to face in different direction causes demagnetization. So if a magnet is heated or hammered several times while it is facing in the east-west direction, it loses its magnetism. Why? Because hammering or heating while facing the east-west direction, it disorients or it disaligns the dipoles within the magnet. It disaligns the dipoles within a magnet. Now, why is it necessary for you to hit it while it is facing in east-west direction for it to be demagnetized? Remember, during magnetization, hammering was also a method. But if you are keen, during the process of magnetization, we were hammering our magnetic material or the steel bar while it was facing in the north-south direction. Why? Because in the north-south direction, that means it is aligned along the Earth's magnetic axis. So that helps the dipoles to remain aligned in one direction. So if you want to disorient or to disalign the dipoles, you actually place the magnetic material, that is the magnetized steel bar, you hit it in a fire, and also you hit it or you hammer it several times while it is facing east-west direction. So it is heated while it is facing in the east-west direction so that it does not retain some magnetism due to the Earth's magnetic field. So remember, if you hit it while it is placed in the north-south direction, actually some of the dipoles could be still aligned by the Earth's magnetic field, because the Earth magnetic field, we did say that it naturally runs from the north towards the south, or it is in the north southern direction. So if you want to disorient or to demagnetize, to demagnetize a steel bar or a magnetized magnetic material, you simply heat it in fire or you hammer it while it is facing in the east-west direction. So we have said that the east-west direction ensures that no dipoles actually are retained, or no magnetism is retained due to the alignment of the dipoles by the magnetic field of the Earth. So that is basically hammering. So you simply either you hit it in fire while it is facing in the east-west direction, or you hammer it several times while it is facing in the east-west direction. So we have said east-west direction so that to ensure that the magnet actually does not retain any magnetism due to the alignment with the Earth magnetic field, which of course faces in the north-south direction. 2, we look at the second method of demagnetizing a magnetic material or a magnetized magnetic material. For this case, we are using actually a steel bar. So if this is our magnetized magnetic material, or if it is just a magnet, then we want to demagnetize it using the electrical method. Remember, we did say that the electrical method was the efficient and the most applicable way and the quickest way of magnetizing a material. Also, when it comes to demagnetization, the electrical method is the quickest and the most reliable methods of demagnetizing a magnetized magnet or a magnetized magnetic material. So electrical method is the quickest and the most efficient. Then in the electrical method, actually the apparatus are arranged as the ones that were used in the actually magnetizing using the electrical method. The only difference is that, one, you ensure that your bar magnet faces in the east-west direction. So the bar magnet is arranged while facing in the east-west direction to ensure that actually no dipoles are realigned by the Earth magnetic field. Then the other thing that changes is that in this case we are using alternating current, that is AC. So if you want to demagnetize, you actually pass alternating current through a solenoid in which we have a magnet actually within it. Remember, for the methods of magnetizing but using electrical method, we were using the same apparatus, but here we are using direct current. Remember, direct current means it is continuous or it does not change from time to time, but alternating current actually keeps on alternating or keeps on changing from time to time. So because of that reversal, it reverses itself from time to time. So because of that continuous reversing, that is what actually disaligns the dipoles, or that is what causes the dipoles to get disaligned. And once the dipoles are disaligned, it means actually the magnet has lost its magnetism. That is based on the domains theory, So in electrical method, an AC, that is alternating current, is passed through the magnet in a solenoid. So this is what we are calling a solenoid. So alternating current, this is our supply of the alternating current. So it is actually alternating current is passed through a solenoid which is placed with its axis pointing in the east-west direction. So you can see actually our magnet here is pointing in the east-west direction. We have said that the reason for making it to point in the east-west direction so that it does not retain any magnetism due to the influence of the Earth magnetic field, which actually points in the north-south direction. So here we are saying that AC is passed, that is alternating current is passed through the magnet in a solenoid which is placed with its axis pointing in the east-west direction. Then the magnet loses its magnetism or the power because alternating current reverses many times per second, hence disorienting or disaligning the magnetic dipoles. So you can be asked to give a reason why alternating current is actually used in demagnetizing a magnet, that is in the electrical method. So the reason is because alternating current reverses many times per second, thereby disaligning or disorienting the magnetic dipoles. Then we are saying that magnets being demagnetized by either the heating or or hammering, and also by the electrical method. So those magnets are usually placed in the east-west direction. So the reason is that so that they don't retain some magnetism due to the Earth's magnetic field. So remember, if you aligned them along the north-south direction, even after demagnetizing, some of the dipoles will still be aligned due to the influence, or they align along the Earth's magnetic axis. But if you are placing it along the east-west direction, it means even after demagnetization, actually the dipoles will still remain disoriented or disaligned. So it is important that the magnets must be placed in the east-west direction. Then we also use alternating current because it reverses many times per second, thereby disorienting actually the dipoles. Then we also look at the difference between hard and soft magnetic material. Now we have certain materials which actually can easily be magnetized, and others will not be easily be magnetized. So we have materials that can easily be magnetized and easily demagnetized, and we have other materials which are hard to magnetize, but once they are magnetized, they actually retain their magnetism. So one of the material, of course, is hard, the other one is soft. But let's look at which material is actually hard or difficult to magnetize. So let's look at the difference between hard and soft magnetic material. So let's start with the hard magnetic materials. So hard magnetic materials, these are actually magnetic materials that are difficult to magnetize but retain their magnetism for a long time. So we are saying that hard magnetic material, these are magnetic materials that are difficult or hard to magnetize but retain their magnetism for a long time. So for hard magnetic material, it is hard actually to magnetize them, or it is not easy to magnetize them. But once they have gained their magnetism, or once they are magnetized, you cannot easily demagnetize them, or they retain or they don't easily lose their magnetism. So hard magnetic materials, these are magnetic materials that are difficult to magnetize but retain their magnetism for a long time. A good example of hard magnetic material is actually steel. Yeah, that's why you saw in our previous experiments we were using steel pins, yeah, or office pins which are actually made of steel. So the reason was because actually steel is a hard magnetic material, or it is difficult to magnetize, but once it has been magnetized, it can retain its magnetism for some time. So we are saying that hard magnetic materials, these are magnetic materials that are difficult to magnetize but retain their magnetism for a long time. An example we are saying is steel. Now, where do we apply the hard magnetic materials, or where are they used? So hard magnetic materials, they are used in making permanent magnets. Hard magnetic materials are used in making permanent magnets. Why do we use them in making permanent magnets? Remember, if you are talking of a permanent magnet, it means it is a magnet that we don't expect it to lose its magnetism easily, or we want it to remain with that magnetism permanently. So that's why we use hard magnetic materials to make permanent magnets, because they retain their magnetism for a long time. So if you are asked to give an application of hard magnetic material, you just say they are used in making permanent magnets. The reason behind that is because they actually retain their magnetism for a long time, hence making the magnet to actually be permanent. Now the other type of magnetic material is what we call soft magnetic materials. Now what are soft magnetic materials? Soft magnetic materials, these are materials that are easy to magnetize but lose their magnetism quickly. So soft magnetic material is just the reverse of what? Hard magnetic material. So soft magnetic material, these are magnetic materials that are easy to magnetize but lose their magnetism quickly. So in short, soft magnetic materials actually do not retain their magnetism for a long time. Although they are easier to magnetize, or they are easier to gain the magnetism, or they are easier to align their dipoles, but once their dipoles have been aligned, it is very easy also to disalign them or to demagnetize them. So soft magnetic materials are those magnetic materials that are easy to magnetize but lose their magnetism quickly. A good example of soft magnetic material is the soft iron actually. So soft iron is a very good example of soft magnetic material. So iron, also we have alloys of nickel. We say that an alloy is just a combination of two or more metals which could have some different properties or close to similar properties. So we are saying that soft magnetic materials, these are magnetic materials that are easy to magnetize but lose their magnetism quickly. An example we are saying is iron. The second example is alloys of nickel. Now, where do we apply or where do we use soft magnetic materials in real life situation? So soft magnetic materials are used in making electromagnets. So later on we'll look at electromagnets. Electromagnet is just a magnet that it does not retain its magnetism. That is a material which can be made a magnet and also be demagnetized very easily. That is, they are not permanent magnets, or in short, they are simply temporary magnets. So soft magnetic materials, they are used or they are applied in making electromagnets. Soft magnetic materials are also used in making transformer cores, and also they are used in magnetic shielding, as we saw in soft iron rod and even the soft iron ring. So if you are asked to give 3 applications of soft magnetic material, is that 1, they are used in making electromagnets, 2, they are used in making transformer cores, and 3, they are used in making in magnetic shielding. They are used in magnetic shielding. Why do we use soft magnetic material in making transformer cores? Because in transformers, we look at another topic in Form 4, which is actually dealing with transformers. The topic, I think, is called it has something to do with actually mains electricity. But we'll see that for a transformer, we have 2 types of transformers. We have what we call the step up and the step down transformers. So in a transformer, we have something we call mutual induction, which requires easy magnetization and demagnetization of the core. So if we want a material that can be easily made to a magnet and also easily lose its magnetism, therefore we'll use a soft magnetic material. But you'll understand that better when we handle that topic in Form 4. So we are saying that soft magnetic materials, these are magnetic materials that are easy to magnetize but lose their magnetism quickly. An example we are giving soft iron and even some alloys of nickel. Then their application, that is application of soft iron, soft magnetic material, is in making electromagnets, 2 making transformer cores, and 3 in magnetic shielding. Then lastly, we look at what we call magnetic storing magnets. That is, how do we store magnets? What is the most effective way of storing magnets? So magnets should be stored in such a way that it does not lose its magnetism. Remember, when you just store it anyhowly, it could lose its magnetism over time through the methods that you have seen up there. That is, for example, the electrical method. You can also have heating and even hammering. So a magnet loses its magnetism. A magnet loses its magnetic strength if not properly stored. Now, what causes demagnetization is 1, repulsion at the poles is actually what causes demagnetization. So if magnets are stored in such a way that the like poles are closer to each other, that means there is repulsion, because from the basic law of magnetism, we did say that like poles would repel and unlike poles will always attract each other. So magnets should be stored in such a manner that the polarities are attracting each other. That is, magnets, if they are stored in such a manner that their polarities are repelling each other, that is, their poles are repelling each other, then that repulsion is what causes demagnetization. So a magnet loses its magnetic strength if not properly stored, and we are saying that repulsion at the poles is what causes demagnetization. Therefore, magnets are stored in pairs with unlike poles adjacent or close to each other, and the pieces of soft iron placed across the end. So these are called what? Keepers. So these are what we are calling keepers. So keepers are made of soft iron materials. Remember, we've just said that soft iron is an example of a what? Soft magnetic material which can easily be magnetized and demagnetized. So we use soft iron simply because they can easily be magnetized and easily demagnetized, or because they are soft magnetic material. So magnets are stored in pairs. In pairs means we store them pair mean two. So you can see we have one magnet here, also another magnet here. So we are storing them in pairs. So magnets are stored in pairs with unlike poles adjacent or close to each other, adjacent, and the pieces of soft iron are placed across the ends. So these are called the keepers. These are called the keepers. These are what we are calling the keepers, or the soft iron keepers. So magnets should be stored in such a way that a north pole is close to a south pole, so that there is always attraction. So you are not supposed to store magnets in such a way that we have a north pole here and also a north pole here. That is, unlike poles should be closer to each other to allow that attraction, because we have said that whenever there is repulsion between the poles is what causes demagnetization. So if you want the magnetization to be retained, then that means you have to store them in such a manner that actually unlike poles are closer to each other, or like poles are further away from each other. Now the keepers become magnetized by induction method. So remember initially keepers are just soft magnetic material, which means they are not magnets. They don't have any magnetism. But when they are brought close to a magnet, they get magnetized. That is by induction method. They are induced with a polarity. We said that in induction, if a material is magnetized by induction, each part that gets in contact with the pole of the magnet actually acquires a polarity that is opposite to that of the inducing pole of the magnet. So if this is a south pole, it will induce a north pole in this keeper. Then if this is a north pole, then it induces a polarity opposite to it, that is a south pole. So because this is a south pole, it induces a north pole. Because this is a north pole, it induces a south pole. So the ion keepers, or the keepers, become magnetized, that is by induction, and their poles neutralize the poles of the magnets. So they neutralize because this is a south pole and a north pole. So these ones will always neutralize each other because they are attracting each other. But they cannot neutralize each other if they are repelling each other. So because this is a north pole, this is a south pole, they attract each other, thereby neutralizing each other. So that neutralization is what retains the magnetism. But actually repulsion actually makes a magnet lose its magnetism. So we are saying that the keepers become magnetized by induction, and their poles neutralize the poles of the magnet. Into bracket, that is the dipoles in the magnet and the keepers form complete loops. So the dipoles within the magnets and the dipoles within the keepers, that is the keepers have been induced with magnetism. So those dipoles actually they form complete loops. So those complete loops help to retain the magnetism. Then you are saying that the dipoles thus retain their orientation or their arrangement, and the magnetism is maintained or retained. So you can be asked to explain how storing magnets using the keepers or soft ion keepers retains the magnetism. So you simply say that when the ion keepers are brought closer to the ends of the bar magnets, they get induced with opposite poles. So that induction with opposite poles, the opposite poles neutralize the poles of the bar magnet, thereby forming closed loops. So those closed loops, or the attraction between the poles, is what retains the magnetism. So anything that causes repulsion at the poles causes what we call demagnetization. Then lastly, we look at the application of magnets. That is, where do we apply or where do we use the magnets in real life situations, or the uses of magnets. So actually magnets have a wide application, but we'll just look at a few of them. One of the application of magnets is that they are used in hospitals to remove pieces of iron from an eye. So you could be in an environment whereby actually an accident can take place and some iron filings can actually spill into your eye. So when the iron filings spill into your eye, when you are taken to the hospital, they just take a magnet. Because an iron filing is a magnetic material, it will actually be attracted by a magnet. So they just take a magnet close to your eye, then it actually attracts. It attracts the iron filing, thereby the iron filing gets out of your eye. So magnets are used in hospitals to remove pieces of iron from an eye. Another application of magnets is that magnets are also used in making compasses. As we saw in our previous class, magnets are used in making compasses. That is because they they align in the north-south direction, that is along the magnetic axis. So that means they can tell you which side is the north pole and which side is the north pole. Then magnets are also used in making loud speakers. Yeah, if you check the loudspeaker or even the speakers of your small radios at home, you will see that that speaker, it has a magnet. So a magnet has its own role there. So magnets are used in making loudspeakers. So we'll discuss the role of that magnet in another topic, which is actually far ahead, or it is just a topic in Form 2 work. You also have another one in Form 4 work, which is actually dealing with things like applications like moving coil meter, the working of a moving coil meter, or even the loudspeakers, or even the telephone receiver. So a magnet is used in making loudspeakers. Then the fourth application of magnet is that magnets are also used in making telephone receivers. Yeah, telephone receivers must have a magnet within them. So we look at those applications, but briefly is that a telephone receiver will always have a magnet with a part called a diaphragm, which actually vibrates as it receives the sound signals, but we'll discuss more about that in another topic in Form 2. Then magnets are also used in making bicycle dynamos. Yeah, a bicycle dynamo in most cases is placed at the rear or the lower wheel of the vehicle, or of the bicycle, which actually rotates in most cases. So the bicycle dynamo is used to generate electricity that powers maybe like the bulb of the bicycle. Yeah, so a bicycle dynamo, so in dynamos you will actually find magnets. So magnets are basically used in production of electricity. You will learn that better in magnetic effect of an electric current, and also in another topic in Form 4, which is actually called the mains electricity. Also under the actually the Faraday's law, you will learn about how magnets are used to generate electricity. Then magnets are also used in generators. Yeah, we have different types of generators. For example, we have what we call the AC generator. We also have the DC generator, that is the alternating current generator, and the direct current generator. Those are topics that we learn in Form 4. Then magnets are also used in electric motors. Yeah, electric motors, remember, they can be used to they can convert that is electrical energy to mechanical energy. That is, they convert the electrical energy in such a way that it starts rotating. Thereby we will see laws like what we call the Fleming's left hand rule, but that is in topics to be covered later. So we have actually come to the end of our class today, but we need to discuss the quote of the day. So the quote of the day simply stated that the teacher has failed more times than the student has ever tried. The only difference is that the teacher chose a better meaning of the word fail, that is first attempt in learning. Remember, fail, I'm giving its initials. So F stands for first, A stands for attempt, I stands for in, then L stands for learning. So failure simply means first attempt in learning. So what does this particular quote mean? So the quote means that in life you have to be willing to learn from your mistakes. So mistakes become our failures only when we choose not to learn from them. Otherwise, all failures are just lessons, but only if we change our perspectives of looking at them. And remember this, that a person who has never failed in life has learned nothing about life. Why? Because you will never learn anything unless you fail. You will never learn anything unless you fail. And also remember this, that life is 1% of what happens to you and 99% of how you react to it. So it doesn't matter whether there are difficult moments happening to you, how you will react to them, that is the attitude you will have those particular problems, is what will determine how your life will actually be. And lastly, choose to be an optimist who sees an opportunity in every difficult moment, but not a pessimist who sees a difficult moment in every opportunity. That is worth repeating. I said, choose to be an optimist who sees an opportunity in every difficult moment, but not a pessimist who sees a difficult moment in every opportunity. This is Kind Tuition Academy, kindly hit that subscription button on YouTube. Thank you.